Elementary algebra encompasses some of the basic concepts of algebra, one of the main branches of mathematics. It is typically taught to secondary school students and builds on their understanding of arithmetic. Whereas arithmetic deals with specified numbers, algebra introduces quantities without fixed values, known as variables. This use of variables entails the use of algebraic notation and an understanding of the general rules of the operators introduced in arithmetic. Unlike abstract algebra, elementary algebra is not concerned with algebraic structures outside the realm of real and complex numbers. The use of variables to denote quantities allows general relationships between quantities to be formally and concisely expressed, and thus enables solving a broader scope of problems. Most quantitative results in science and mathematics are expressed as algebraic equations. Algebraic notation. Algebraic notation describes how algebra is written. It follows certain rules and conventions, and has its own terminology. For example, the expression has the following components: 1. Exponent, 2. Coefficient, 3. Term, 4. Operator, 5. Constant. Variables. A coefficient is a numerical value which multiplies a variable. A term is an addend or a summand, a group of coefficients, variables, constants and exponents that may be separated from the other terms by the plus and minus operators. Letters represent variables and constants. By convention, letters at the beginning of the alphabet are typically used to represent constants, and those toward the end of the alphabet are used to represent variables. They are usually written in italics. Algebraic operations work in the same way as arithmetic operations, such as addition, subtraction, multiplication, division and exponentiation, and are applied to algebraic variables and terms. Multiplication symbols are usually omitted, and implied when there is no space between two variables or terms, or when a coefficient is used. For example, is written as, and may be written. Usually terms with the highest power are written on the left. For example, is written to the left if. When a coefficient is 1, it is usually omitted. Likewise when the exponent is 1. When the exponent is 0, the result is always 1. However, being undefined should not appear in an expression, and care should be taken in simplifying expressions in which variables may appear in exponents. Alternative notation. Other types of notation are used in algebraic expressions when the required formatting is not available, or cannot be implied, such as where only letters and symbols are available. For example, exponents are usually formatted using superscripts, e.g., in plain text, and in the text markup language, the caret symbol, caret, represents exponents, so is written as x squared. In programming languages such as Ada, Fortran, Perl, Python and Ruby, a double asterisk is used, so is written as x asterisk asterisk 2. Many programming languages and calculators use a single asterisk to represent the multiplication symbol, and it must be explicitly used. For example, is written 3 asterisk x. Concepts. Variables. Elementary algebra builds on and extends arithmetic by introducing letters called variables to represent general numbers. This is useful for several reasons. Variables may represent numbers whose values are not yet known. For example, if the temperature today, T, is 20 degrees higher than the temperature yesterday, Y, then the problem can be described algebraically as. Variables allow one to describe general problems, without specifying the values of the quantities that are involved. For example, it can be stated specifically that 5 minutes is equivalent to seconds. A more general description may state that the number of seconds, where m is the number of minutes. Variables allow one to describe mathematical relationships between quantities that may vary. For example, the relationship between the circumference, c, and diameter, d, of a circle is described by. Variables allow one to describe some mathematical properties. For example, a basic property of addition is commutativity, which states that the order of numbers being added together does not matter. Commutativity is stated algebraically as evaluating expressions. Algebraic expressions may be evaluated and simplified, based on the basic properties of arithmetic operations. For example, added terms are simplified using coefficients. For example, can be simplified as multiplied terms are simplified using exponents. For example, is represented as like terms are added together. For example, is written as because the terms containing are added together, and the terms containing are added together. Brackets can be multiplied out using distributivity. For example, can be written as, which can be written as. Expressions can be factored. For example, by dividing both terms by, can be written as equations. An equation states that two expressions are equal using the symbol for equality. One of the most well-known equations describes Pythagoras' law relating the length of the sides of a right-angled triangle. This equation states that, representing the square of the length of the side, that is the hypotenuse, is equal to the sum of the squares of the other two sides whose lengths are represented by an. An equation is the claim that two expressions have the same value and are equal. Some equations are true for all values of the involved variables. Such equations are called identities. Conditional equations are true for only some values of the involved variables, e.g., is true only for n. The values of the variables which make the equation true are the solutions of the equation and can be found through equation solving. Another type of equation is an inequality. Inequalities are used to show that one side of the equation is greater or less than the other. The symbols used for this are where represents greater than and where represents less than. Just like standard equality equations, numbers can be added, subtracted, multiplied or divided. The only exception is that when multiplying or dividing by a negative number, the inequality symbol must be flipped. Properties of equality. By definition, equality is an equivalence relation, meaning it has the properties reflexive, symmetric, transitive. It also satisfies the important property that if two symbols are used for equal things, then one symbol can be substituted for the other in any true statement about the first and the statement will remain true. This implies the following properties: if and then in, if then. More generally, for any function, if then. Properties of inequality. The relations less than and greater than have the property of transitivity. If and then, if and then, if and then, if and then. By reversing the inequation, and can be swapped. For example, is equivalent to substitution. Substitution is replacing the terms in an expression to create a new expression. Substituting 3 for in the expression or *5 makes a new expression 3*5 with meaning 15. Substituting the terms of a statement makes a new statement. When the original statement is true independent of the values of the terms, the statement created by substitutions is also true. Hence definitions can be made in symbolic terms and interpreted through substitution. If, where, equals means, is defined to equal, substituting 3 for informs the reader of this statement that means 3*3 equals 9. Often it's not known whether the statement is true independent of the values of the terms, and substitution allows one to derive restrictions on the possible values, or show what conditions the statement holds under. For example, taking the statement x plus 1 equals 0, if x is substituted with 1, this implies 1 plus 1 equals 2 equals 0, which is false. Which implies that if x plus 1 equals 0 then x can't be 1. If x and y are integers, rationals, or real numbers, then x y equals 0 implies x equals 0 or y equals 0. Suppose ABC equals 0. Then, substituting A for x and BC for y, we learn A equals 0 or BC equals 0. Then we can substitute again, letting x equals b and y equals c, to show that if BC equals 0 then BE equals 0 or C equals 0. Therefore, if ABC equals 0, then A equals 0 or, so ABC equals 0 implies A equals 0 or BE equals 0 or C equals 0. Consider if the original fact were stated as AB equals 0 implies A equals 0 or BE equals 0, then when we say, suppose ABC equals 0, we have a conflict of terms when we substitute. Yet the above logic is still valid to show that if ABC equals 0 then A equals 0 or BE equals 0 or C equals 0 if instead of letting A equal certain BE equals BC we substitute A for A and B for BC. This shows that substituting for the terms in a statement isn't always the same as letting the terms from the statement equal the substituted terms. In this situation it's clear that if we substitute an expression A into the A term of the original equation, the A substituted does not refer to the A in the statement. AB equals 0 implies A equals 0 or BE equals 0. Solving algebraic equations. The following sections lay out examples of some of the types of algebraic equations that may be encountered. Linear equations with one variable. Linear equations are so called because when they are plotted, they describe a straight line. The simplest equations to solve are linear equations that have only one variable. They contain only constant numbers and a single variable without an exponent. As an example, consider problem in words. If you double my son's age and add 4, the resulting answer is 12. How old is my son? Equivalent equation, where represent my son's age. To solve this kind of equation, the technique is add, subtract, multiply, or divide both sides of the equation by the same number in order to isolate the variable on one side of the equation. Once the variable is isolated, the other side of the equation is the value of the variable. This problem and its solution are as follows. In words, my son's age is 4. The general form of a linear equation with one variable can be written as following the same procedure. The general solution is given by linear equations with two variables. A linear equation with two variables has many solutions. For example, problem in words. I am 22 years older than my son. How old are we? Equivalent equation. Where is my age? Is my son's age? This cannot be worked out by itself. If I told you my son's age, then there would no longer be two unknowns, and the problem becomes a linear equation with just one variable. That can be solved as described above. To solve a linear equation with two variables, requires two related equations. For example, if I also revealed that now there are two related linear equations, each with two unknowns, which lets us produce a linear equation with just one variable, by subtracting one from the other. In other words, my son is age 12, and as I am 22 years older, I must be 34. In 10 years' time, my son will be 22, and I will be twice his age, 44. This problem is illustrated on the associated plot of the equations. For other ways to solve this kind of equations, see below. System of linear equations. Quadratic equations. A quadratic equation is one which includes a term with an exponent of 2, for example, and no term with higher exponent. The name derives from the Latin quadrus, meaning square. In general, a quadratic equation can be expressed in the form, where is not 0. Because of this, a quadratic equation must contain a term, which is known as the quadratic term. Hence, and so we may divide by and rearrange the equation into the standard form where n Solving this by a process known as completing the square leads to the quadratic formula, where the symbol plus or minus indicates that both are solutions of the quadratic equation. Quadratic equations can also be solved using factorization. As an example of factoring, which is the same thing as it follows from the zero product property that either or are the solutions, since precisely one of the factors must be equal to zero. All quadratic equations will have two solutions in the complex number system, but need not have any in the real number system. For example, has no real number solution since no real number squared equals -1. Sometimes a quadratic equation has a root of multiplicity 2, such as, for this equation, -1 is a root of multiplicity 2. This means -1 appears 2 times. Since the equation can be rewritten in factored form as complex numbers, all quadratic equations have two solutions in complex numbers, a category that includes real numbers, imaginary numbers, and sums of real and imaginary numbers. Complex numbers first arise in the teaching of quadratic equations and the quadratic formula. For example, the quadratic equation has solutions since is not any real number. Both of these solutions for x are complex numbers. Exponential and logarithmic equations. An exponential equation is one which has the form 4, which has solution when elementary algebraic techniques are used to rewrite a given equation in the above way before arriving at the solution. For example, if then, by subtracting 1 from both sides of the equation, and then dividing both sides by 3 we obtain whence. Or a logarithmic equation is an equation of the form 4, which has solution. For example, if then, by adding 2 to both sides of the equation, followed by dividing both sides by 4, we get whence, from which we obtain radical equations. A radical equation is one that includes a radical sign, which includes square roots, cube roots, and nth roots. Recall that an nth root can be rewritten in exponential format, so that is equivalent to, combined with regular exponents, then, can be rewritten as. So a common form of a radical equation is wherein are integers. It has real solution. For example, if, then, system of linear equations. There are different methods to solve a system of linear equations with two variables. Elimination method. An example of solving a system of linear equations is by using the elimination method, multiplying the terms in the second equation by 2, adding the two equations together to get, which simplifies to since the fact that is known. It is then possible to deduce that, by either of the original two equations, the full solution to this problem is. Then note that this is not the only way to solve this specific system, could have been solved before. Substitution method. Another way of solving the same system of linear equations is by substitution. An equivalent for can be deduced by using one of the two equations, using the second equation, subtracting from each side of the equation, and multiplying by -1. Using this value in the first equation in the original system, adding 2 on each side of the equation, which simplifies to using this value in one of the equations. The same solution as in the previous method is obtained. Note that this is not the only way to solve this specific system. In this case as well, could have been solved before. Other types of systems of linear equations. Inconsistent systems. In the above example, a solution exists. However, there are also systems of equations which do not have any solution. Such a system is called inconsistent. An obvious example is as 0, 2. The second equation in the system has no solution. Therefore, the system has no solution. However, not all inconsistent systems are recognized at first sight. As an example, let us consider the system multiplying by 2 both sides of the second equation, and adding it to the first one results in which has clearly no solution. Undetermined systems. There are also systems which have infinitely many solutions, in contrast to a system with a unique solution, for example, isolating in the second equation, and using this value in the first equation in the system. The equality is true, but it does not provide the value for. Indeed, one can easily verify that for any there is a solution as long as there is an infinite number of solutions for this system. Over and underdetermined systems. Systems with more variables than the number of linear equations are called underdetermined. Such a system, if it has any solutions, does not have a unique one but rather an infinitude of them. An example of such a system is when trying to solve it, one is led to express some variables as functions of the other ones if any solutions exist, but cannot express all solutions numerically because there are an infinite number of them if there are any. A system with a greater number of equations than variables is called overdetermined. If an overdetermined system has any solutions, necessarily some equations are linear combinations of the others.